This is a presentation on ad hoc sensor nets and software-defined radio used in a REL environment. Yeah, my name is Michael Alldritt, and I'm a PhD candidate at UTS and also a senior project engineer at Laing O'Rourke. So my work career is included communications utilities across the world, Ireland, Australia. I've worked for Hitachi and MTS, and I'm currently working for Laing O'Rourke. So my research at University Technology Sydney started in 2019 and extended from an idea using audio to transmit data using ultrasound. So the Ad Hoc Shipping Network project was initiated by my supervisor, Professor Robin Braun. My objective was to create a working prototype using GNU radio to modulate and demodulate data at 40 kilohertz in air, water, and steel. And the original concept was theoretical in nature, to create nets using modulated ultrasound. The software solution was novel and innovative with many benefits. So communications devices could connect to each other to form networks. Nodes could be created when a certain number of connections had been made. And the application was considered revolved around shipping containers with sensitive and precious cargo. So these freight normally had high monetary value. The environment inside a container could be continuously monitored, so that it was not damaged. Sensors would capture temperature, humidity, air quality, gas, preventing vibration, radiation if required. So as you can see from the diagram there, like shipping containers on ships, they're packed like really quite high. And so one of the issues about that is that when you're trying to communicate with the outside world with this information, if you're using a 4G modem, and if your container happens to be the one on the inside, it won't be able to communicate to the outside world because RF doesn't communicate through these if it's surrounded by other metal containers. So, however, audio waves will travel very well through metalwork, and you could create two devices, a device that will communicate through the metalwork using audio waves, and then to a node that will actually use a normal EM wave. So the same issue as well for freight trains, where you have like a number of containers all on a very long train. There's no network in a lot of the rural and remote areas. So you need to have a way to communicate, especially if you've got sensitive or precious freight. So each metal car would basically have so all the containers are in metal cars. They're all connected to each other by coupling. And if each one of these containers had a device that could, like a shipping container radio, that could modulate and demodulate, the sound waves would propagate through the steel for the short distance, and every freight metal enclosure on each railway car, they all would communicate. And the concept behind how ad hoc networks could be created using GNU radio is a way to exchange data between these devices. And if a container generates an alarm because the sensors detect heat, then the driver, for example, of the train could actually do something about it. So basically, how you're actually propagating data, you're using an ultrasonic transducer, and the sound wave, the energy causes the piece of ceramic plate to vibrate if it's on the receive side, and if it's on the transmit side, you're actually converting that electrical signal into an audio signal. So the electrical signal is amplified and resampled to create a complex data stream, and the software block in GNU radio filters out the unwanted components of the signal. So the part that remains is the data stream, and the stream has to synchronize with the receiver. So you need to have a preamble that will actually, tell the receiver where to actually start when it's correlated and where to actually begin the data read. And if all goes well, the data is captured and can be opened to read the message, to see the image or hear the audio. So one of the things about, like, as opposed to electromagnetic waves, so at 40 kilohertz, an EM wave would have to have a wavelength of about 7,500 meters, which is quite long. But for audio, that wave would be in air, it would be 8.5 mil or 37.5 mil are 148 mil if between in steel. Now the speeds that audio waves travel, like in air, it's 340 meters per second. In water, it's about 1500, and about in steel, it's about 6,000 meters. And the wave itself elongates when it actually changes from one medium to another medium. So there's some issues with that can cause data loss. So this is just a short video. It just shows you how the actual, you can see how fast the audio wave will propagate through steel. And when I play that, it's really, really fast. And then when it goes through air and water, like in air, it's like just pretty slow, right? But it just shows the actual the difference in speed. Like I think sound propagates through steel nearly 20 times faster. So next up, so when you're using audio waves, in normal EM waves, it's a transverse wave, but in audio, you can have both a transverse and longitude waves. It can be both. So some of the modulation techniques, on-off keying, right, which is a very basic way of doing things, which is quite good. So our amplitude shift keying, but BSAK is the same as off-off keying. Frequency shift keying is another very good, using a mark and space for the 0 and 1. You can actually have a QFSK, but that requires a bit more bandwidth, and the same with phase shift keying. You know, you if you want to have like 4 frequencies, you need QPSK, which takes up a little bit more bandwidth, and we have very limited bandwidth. It's only really from 39 kilohertz up to 41. So I did a signal noise ratio test, and the actual, you can see on this that the actual I'm getting nearly 30 dB above background, which is great when it's close together. This is again in air, but the signal to noise ratio is fantastic. So some tests that I actually performed. So first of all, some rail track that I actually did some testing on to begin with, using two Raspberry Pis and Ubuntu GNU Radio, using a bit of rail, and I basically put the transducers on both ends, and I sent a data set from one side to the other, and I got very, very good results from that. Now, again, it was a data set, so it wasn't actually real data in a real, like a file that you're transmitting. But it was still okay. It showed that everything, the data was actually being received properly, and it was being sampled correctly. And I demodulated and displayed it on the monitor. It did a comparison. It was exactly the same. Did use the 3 different modulation techniques. However, ASK or double on-off keying was pretty much the best result. So, this is another test I did. This is showing using it in air. So this is basically some files that I used for transmitting and receiving, and they're basically modulated files that Barry Dugan created, and they work really well for this application. So, the first thing was using software with a preamble. I tried using text, and the preamble allowed the receiver to synchronize, and it correlated straight away. The transmit receive rate, was 120 baud. And the file source was about 2 kilobits. So it took about 2 or 3 minutes for this to transmit. I used the Gettysburg address, and it worked really well. So, all right, the next bit was basically just actually, I decided to do an image, and this was at 1200 baud, so I transmitted the image again, and it was in air, so I'll just play this. Okay, so what I've done is I've set up again, like to have another go. I've created 2 new leads because I wasn't having much success with the transmitting it through rail. So I've got 2 40 kilohertz transducers. They're actually going through this particular sound card. I've got an empty output.temp, and I've got an output2.jpg, and what's in that file is basically
this is my target, and it's actually just the blue screen of, So now what I'm going to do is I'm going to move this file, which is giraffe2.jpg, and I'm going to transmit it from the left to the right. Okay. So the first thing I'm going to do is I'm going to just make sure that I've got both of my things ready to go. So I've got to actually open up the receive first. So I'm going to go receive. Okay, now this is actually set to transmit at 1.2 kilobits. One thing I noticed before, the correlation did it straight away. I could not get it to collate earlier, right? And no matter how hard I tried, I could not get it to work. So we have good data flow, which is fantastic. This takes about 3 or 4 minutes.
So rather than waiting to see data transfer, I'll actually just advance it a little bit.
34.
So to get towards the end where you can actually see the actual file convert. So I'll just move it up to about here. So this is pretty much getting towards the end of the actual data flow, and you can see that it's actually the preamble has actually finished.
Last bit of data is done, so that's completed in just under 8 minutes. So I'm going to, now that that's done, I'm going to close the transmit. I'm going to close the receive. My data that's been transmitted is 52.7, so there's quite a bit, there's a bit of the preamble in there as well. That's all the preamble. So now what I'm going to do is I'm going to come back to, and this is receive, and then I'm going to go to convert it, and watch when as soon as I actually press return, what will happen is the output2.jpg will change, right? And there it is. So what that means is I have transmitted the giraffe from one to the other.
Yeah, so but that's in air, so it doesn't really count, does it? I mean, you can just actually use RF for that. However, so this is basically the transmission. So I've got the actual target with blue screen, nothing like it to actually overwrite, and then the actual image of the giraffe. So then I thought the next step of that is to actually do this in water. So I set up a little water bath, and I actually set it again, same sort of thing. And I transmit it. So this is the second one. Again, it was at 1200 baud.
What I'm going to do at the moment is I've got this in water.
I did it a number of times. They're not actually, they're not touching, even though it might look that way.
Give it a go. So we've got set up. We've got our sound card, 2 ultrasonic transducers sitting in water, right? And they are not touching, as you can see, but they are sitting in water.
I had to mention that.
So this is what I have at the moment, and I'm going to send a picture of a chimp, right? Which is in my receive file. It looks a bit like this, right? So I'm going to send it from one side to the other, and it'll replace that output too. So I'll get my files open again. Okay, so over on this side, I'm going to run the receive. Okay, so that starts that side up. On this side, I'm going to run the transmit. Which is that one. And as you can see, it correlated pretty much straight away, right? Which is surprising because it is sitting in water, right? Now, in the end, I found it was just best just to dump it straight in the water, and then it worked.
Yeah, sometimes it's better not to try and line it up. It just put it straight in.
Set it up in any way. So correlations worked. That's very good. And it takes maybe a couple of minutes.
So I did this with a number of different file sizes, and
as you can
with
see,
various successes.
Right, and it seems to be transmitting okay. So we just got to give it a few minutes. So this is really the first successful transmission in water, right, that I've had. So we'll see how it goes. As I said, it'll take a couple of minutes, and we've just started maybe a minute ago, so it'll probably take about 4 minutes.
Yes. So one of the issues I had with this was basically if you move the transducers around, it actually caused the signal to actually deteriorate. So that they had to be not interfered with during the transmission.
It seems to be,
but
transmitting.
I did it a number of times with a number of different file sizes,
but it's still
and
transmitting.
it was successful most of the time, except when I moved the transducer.
And on this side we have, our TX all going through very well. And this side is good. It took such a long time to get it to correlate, but it did eventually.